Good morning, good afternoon, and welcome to part 2, the sequel of Electron Configuration, where we will focus on orbital diagrams and everyone's favorite quantum numbers. But before we do that, let's talk about this sheet. When you get your next test, rip the back page of the test off, as you're instructed to do in the Read Me First box, so I know you guys do that. And then I would do what we talked about last time. S, P, D, F, and then just go 1, 2, 3, 4, and just count as you go down and put those in. Bring a crayon, bring a marker, something to test, something that's obvious. And if you're astute, you'll notice I did a couple other things. Again, the chutes and ladders for the lanthans and actans, don't forget they're down there. And then I also did some of the quantum numbers, and this is going to come into play in what we're about to do. Notice I put L as 0, 1, 2, 3 as S, P, D, and F. Then I put the maximum number of, or the orbitals in a subshell. Sorry, that's not maximum, that's an always. S's always come in sets of 1, P's in 3, D's in 5, F's in 7. Now, the electrons are a maximum. Maximum electron. Again, there can be 0 or up to this number. 2 in an S, 6 in a P, 10 in a D, 14 in F. If you forget, just count. S block is 2 wide, hence 2 electrons. P is 6 blocks wide, 6. D is 10, 10, F is 14, 14. You can just count, literally. Okay, so I would highly suggest doing this for testing purposes, practice purposes, etc. All right. Back to where we left off. Say you want to do the orbital filling diagram, and I gave you the element like platinum. First thing, of course, you've memorized. Platinum is PT. Then you would find it on the PT. Periodic table, that is. And then you would do what I said before. You would go backtrack until xenon, and then go 6s2, 5d8, and then don't forget down here 4f14. So I've done that for us here, reinforcing this idea of the core electrons, unreactive, nothing happens, boring, nothing to see, move along. The valence electrons, excitement, stuff happens, we gain them, we lose them, it's very exciting. What happens with those valence electrons? So, orbital filling diagrams are typically going to just look at the valence. Now we could, in theory, do all of them. You might even do space filling. We had 1s at the bottom, then 2s, then 2p, and you get the idea. But so how do we represent this? So each subshell is going to get its own set of dashes. So s's always come in sets of, man, I don't remember. Oh, it's 1. I got it there. So we write 1 dash. F is 7. 1, 2, 3, 4, 5, 6, 7. D's are 5. So we write 1 dash for each, and then if I'm spacing correctly, the letter goes under the center orbital. So you have the 6s, 1 dash, 4f with 7, 5d with the 5. And then these become the electrons. 1, 2. Remember, each one has to be unique. Pauli exclusion principle. We have fill and match spin, Hund's rule. So if we have 14, I'm going to fill them in the order they would actually fill. And although there's multiple ways we can do this, it's going to look something like this. So, first electron we can put anywhere we want, and we can have it spinning any way we want. Doesn't matter. Now, I'm a creature of habit. I work down and left. So let me get rid of this. But there's nothing wrong with, you can put the first electron wherever you want. Second electron, we have 4 choices. We can put it wherever we want, but we have to match that spin. So that's fine. That's fine. That's fine. That's fine. And now with the 6th electron, again, doesn't matter where we put it, but we have to flip the spin because it's got to be different. So I usually just work down and left, up and then back, going up. So that would be 6, 7, 8. That would be a correct answer. Although, to be honest, there's nothing wrong with this answer. There's also nothing wrong with this answer. So again, there's more than one correct electron configuration that satisfies our 3 rules and would be considered a ground state electron configuration. Now, there are 2 other things I kind of forgot to mention. There are a couple exceptions to what I taught you off the periodic table. The whole F block is an exception that I'm going to ignore. I'm aware of it, but I'm going to ignore it. But there's a couple in the D block that really do. So chromium, for example, this is the correct electron configuration, which would be 4s1, 3d5. we would predict by the Aufbau principle it to be this, which it's not. So why is this a violation of the Aufbau principle? And what's happening here is the equal distribution of the electron field, or the electronic field, the magnetic field. If we were to go with this configuration, and this gets into why are noble gases stable, it's not because of eight, it's not because it's magic, it's because they have equally distributed all their electrons, all the charge, all the magnetic field. There aren't weak spots and hot spots within that. It's a nice, clean, consistent filling spin. So there is no reactive surface. So this, again, this is leaving a hole where we have no electron density. That's a positive spot, hot spot if you want for reactions, where this is equally distributed. So it takes a little bit of energy to move this up, but we gain that energy back in what they call the electron pairing energy, which is not all that important for this course, but I do expect you to realize that we can do this to pop it over to make it all half full. Your most stable states are completely empty, completely full, and half full. So where else would this occur? Same thing would happen in the same family, so with chromium and molybdenum. And then we also see the same thing at the end with copper, silver, and gold. Where in that case you get S1D10, where this is S1D5. So one of the S's gets moved over to completely fill the d orbital, again leaving states that are completely full, completely empty. Other things I like to ask is, how many 2p orbitals does hydrogen have? And if you find hydrogen up here and you say the electron configuration for hydrogen is 1s1, you're correct. But if you say it has no p orbitals, you're wrong. It has no p electrons. But the correct electron configuration, if you remember the line spectrum, so we know this, there's evidence of this, this would be your correct electron configuration for hydrogen. They're all there, they're just empty. So it doesn't even matter what I put here. The answer for any p subshell, the answer is always 3. Again, it could be empty, could be full, could be partially full, but the answer for how many orbitals in a 2p subshell element doesn't matter, it's 3. So just that as kind of a quickie reminder. And I felt like there's one other thing. Oh, so what would you do if something had a positive charge? So let's say we had platinum 2+. You literally just take off the last 2 electrons. And that's how you would adjust the electron configuration for a positive charge. Likewise, if you had something with a negative charge, you would just do the normal electron configuration. Don't save too much there. And you would add those 2 electrons. And that's all you would do to adjust for a charge. So I think that's pretty straightforward. Or you just pretend, instead of oxygen, just pretend it's neon. Or instead of platinum, take 2 electrons away, pretend it's osmium in the periodic table. So just adjust that way. So I think that's pretty straightforward. And I think orbital diagrams in general are pretty straightforward. So just realize, as long as it meets the rules, it doesn't matter if it looks nice. Like this is also fine. Might look a little funny because we left a gap, but it's totally fine. It meets the rules. Half filled as many orbitals as possible, and we match those spins. And this would be a course called paramagnetic. It doesn't matter that all of these are full. It doesn't matter that all of these are full. As long as we have a single unpaired electron, we know it's a paramagnetic molecule. Okay, quantum numbers. Write a consistent set of quantum numbers for the valence electrons of silicon. I like to put this on the test. When you see this question, I want you to go through and do essentially 4 things. Number 1, write the noble gas configuration for silicon. So I find silicon, I go back on the periodic table, I find neon, 3s2, 3p2. So not so bad. Number 2, once you have the noble gas, I want you to do what we just did with the orbital filling diagram. So 3s, 3p, s's always come in sets of 1, p's always come in sets of 3, and those are my 2 orbital sets. Now I'm going to put in my electrons, and I told you I'm a creature of habit. I work down with my arrows and I go left to right, so I'm just going to put this as my electron configuration. If you understand what this picture is showing you, you have your quantum numbers. So what do I mean by this? So next thing we have to do is pick an electron. So I'm going to pick this one right here to talk about. And then we're going to find our 4 quantum numbers. They're already up here on the board. We just might not realize it. This 3 is our principal quantum number, and this S is our second quantum number. So we have those numbers already. So it's going to be 3 comma, and then remember, 0, 1, 2, 3, SPDF, so S is going to be 0. If you're wondering why I asked you to put this on your piece of paper at the beginning, it's probably making more sense now. I'm going to skip the third quantum number because that's a little tricky. Then we just look at the arrow. The arrow is pointing down, so that's -1/2. And then last thing is, what's the orbital it's in, the specific orbital? Remember, shell, subshell, orbital, electron. So we want to know the actual dash. Without knowing quantum selection rules, the easiest way to do this is take the center orbital of the subshell and put a 0 over it. And then count until you're out of orbitals. So I'm going to go +1, negative direction, -1, and you've now correctly determined your M sub L values or your third quantum number. So in this particular case, just look up, I see a 0, I'm good. Now pick another electron. Continue, repeat. So now I'm going to move over and take this second electron right here. We're going to do the same thing, it's still 3, still S, still with a 0 over it, except now it's pointing up, so I'm going to call it +1/2. Hopefully this is starting to make some sense. Pick another electron. It's in the 3, so it's still 3. It's in the P, that gets coded as a 1. I look up, I see -1. I just write that down, I don't even think about it. It's pointing down, I write -1/2. Take this last electron. It's still a 3, still a P. It's got a 0 above it, it's still pointing down. And I now have a consistent set of quantum numbers that answers the question. It's not the only answer. I could have just as easily drawn this. In which case this would be +1/2 and +1/2. That would be just fine. As long as these numbers match and these are different, we're A-okay. The others have to pretty much be locked into where they are. So what happens if we flip this around? Sometimes this throws people. The following represents the valence electrons for which element? So what is this really doing? So number one thing you need to realize is each of these is an electron. Electron, 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 electron. So we have 4 electrons. Next thing you want to do is, if you're thinking about SPDF notation, that's your subshell, that's the first 2 numbers. So 4 is 4 and 0 is S. So I have 2 4 zeros. I have 2 5 2s. And the rest of this I don't even care about. It doesn't matter. And that's it. So then I go to the periodic table. I find the D. I find the 5. I count 2 blocks in. I see hafnium. Kind of an odd choice. Boy, I would have preferred... Okay. I make mistakes. This was supposed to be a 3. I went the wrong way. I knew I had to change the number by 1. What I just wrote doesn't exist. Let's try this again. I find the D, I find the 3, I count 2 blocks in, I get titanium. Sorry about that, that should have been 3 the whole time. Same principle. Number, letter, number, letter, number, letter, number, letter. See how many you have of each combo. I have 2 of those, so I put a 2. I have 2 of those, I put a 2. If I had had a third one, 3, 2, minus 1, a half, that would be another electron, and it would be D3, and we would just go over to the next block, which would be vanadium. And with that, victory over chemistry, and peace out, my friends.